Okay. So there was a little more on making Lewis structures. There's stuff called formal charge and resonance structures that I didn't quite get to. So there was rule 1, 2, and 3 for making those Lewis structures. And then when you got to rule 4, you sometimes had an expanded octet on the central atom. What was the other thing? Oh, sometimes you had a less than an octet on some atoms. So we started to run into some of the complicated things that can come up, and I didn't quite get to the rest. And since my screens are down, I'm just not going to try to finish that out. There's another subject of polarity that I need to go over related to molecular bonds. And then that all leads into this thing called molecular shape. But instead of going that route, because I've lost my screens today, I'm going to go ahead and show you what molecular shape is. So let me write that up. And this is important. The word molecular shape is a little bit of a misnomer. Everybody have a periodic table? I think you'll want one. Okay, those of you who took chemistry before, do you remember the phrase molecular shape? Any of you remember molecular shape? Okay, if you covered it in high school or wherever, you remember it was. Tetrahedral, square planar, all that stuff. Okay. Let me give you what is, I think, the simplest version of this, because you can kind of just memorize these. Here's your periodic table of the nonmetals. I'll include boron because it's a metalloid and it sometimes shows up in molecules. E, C, N, O, F. I'll put neon here, but we won't deal with these. And of course, we've got phosphorus, sulfur, chlorine, bromine. Where's my periodic table? I guess I'll include selenium and iodine, phosphorus, selenium, selenium, phosphorus, selenium, iodine, and then these are the noble gases. And really, it's just those I want to focus on. And again, molecular is kind of a misnomer. I wish chemists didn't use that. What we mean is the shape around an atom in a molecule. So it's not the shape of the overall molecule that we're talking about. We're talking about shape of individual atoms when they're in a molecule. So it's a bit of a misnomer. It's unfortunate. But that's chemistry. There's always weird little twists. Okay. And just like before, whatever I say for nitrogen goes for whatever's below it. And if I'm going to stop on just the nonmetals, I would stop on phosphorus. And same here and same here. So I'm going to cover, I'll start with carbon because, again, it's really these that are the most common atoms that we deal with. Really, it's just carbon, nitrogen, and oxygen. But anyway, let me just cover those, and then whatever I say for those actually goes for everything below it. Maybe silicon here. All right, let me put it this way. We talked last time about carbon You recognize that, right? What I just drew, what is that? Yeah, the Lewis dot structure. But let me go ahead and go, you can have a bond there, you can have a bond there, you can have a bond there, and you can have a bond there. So for this discussion, what I want you to notice is there's an atom there, some atom. Okay, and now we go over to nitrogen, and what I would have drawn is that for the dot structure, but no atom connects here. That pair of electrons just stays there. Those are paired. These get paired by making bonds. And you've got an atom here, and we'll go on across to oxygen. That one had two pairs, and then dots like that. Let me draw. These will become bonds. Atom there. And I'll finish it out with fluorine. That's what fluorine would be, but I'll draw this out and see. Atom there. Okay. I want to expand this picture a little bit because I did allude to the fact that there are double and triple bonds. So let me draw carbon in a situation where it's making double bonds to something. Double bond to an atom, and then atom there. Double bond like that, okay. So you also might see carbon double bond. So it's still four bonds. It's just this one of the bonds is a double bond. So there's still four bonds. Four bonds, four single bonds. Two single bonds, one double bond. Two double bonds, and there's also carbon triple bond to some other atom. That's in total the four different ways you'll see carbon in a molecule. You with me? There's no other way you're going to see carbon in a molecule. It's either going to be a triple bond. So this is still four bonds, but it's a triple bond and a single bond. This is still four bonds, but it's a double bond and a double bond. This is still four bonds, double bond, two single bonds, and here's four single bonds. You with me? You're with me. It isn't any more complicated than that. You can have nitrogen with all three single bonds, or you can have nitrogen with a double bond and a single bond. This pair of electrons is still there, though. So I'm going to say atom, atom, and a pair of electrons. And you can actually see nitrogen with a triple bond and a pair of electrons to an atom. Those are the three ways you will see nitrogen in a molecule and no others. Yes, three bonds, one triple bond. Yes, three bonds, a double bond, and a single bond. Three single bonds, three bonds. Those are the ways you'll ever see nitrogen. There will never be any other way in the molecule. And getting a little more simple, oxygen, I'm going to draw it down here. Oxygen can form a double bond with its two bonds. And I'm going to put that up here. Oxygen to an atom. There's oxygen. What am I doing? Okay. Pair of electrons, pair of electrons. And that. And this is the only way you're going to see chlorine. It only makes one bond, so there's no double bond situations and triple bond situations. So if you just kind of memorize that, everything I said for nitrogen is true for phosphorus. Everything I said for oxygen is true for lipids. Everything I said for carbon is true for silicon. It shows up in molecules, just not as often. Same for all of these. These all behave like fluorine. So it's just those set of examples gives you all the nonmetals. And since this is all about molecules, which is all about only nonmetals, that's really a complete list. That helps. This is the simple way to see this. The next step is I'll show you Lewis structure, and you have to look at the atom and tell me something about it. That is, tell me the molecular shape. Let me condense this because I want to leave those there, but I need room to work. Hydrogen, boron, carbon, nitrogen, oxygen, fluorine. I think I'll just leave those on. Silicon, phosphorus, sulfur, chlorine, bromine, iodine, and I'll stick in selenium. Okay, so these are pretty much all the nonmetals. Hydrogen is like fluorine. It only makes one bond, but there are no pairs of electrons around it. Let me start with these across the top, not counting hydrogen. Let me just stick hydrogen up here. It's always its own case. Atom there, atom there, atom there. I think putting spheres here will help with your visualization. Maybe I should open up a little room. Okay, let me point out for this top row. For that top row, there are 4. For all of these in the top row, there are 4 things around the atom. Around carbon, there happens to be, the 4 things are all atoms. Around the nitrogen, 3 of the things are atoms. 1 of them is a pair of electrons. That's still 4 things. So by things, I mean atom or pair of electrons. That's what I mean by things. It's either an atom or a pair of electrons. But it's still 4. Here there's 2 atoms, 2 pairs of electrons. Here it's 1 atom and 3 pairs of electrons. When there are 4 things around the atom, we call that tetrahedral. And that's the main point, really. I should have put it in parentheses, but it's like it's insignificant. That means tetrahedral. All of these atoms in that particular bonding state we call tetrahedral. Things I'll use the more fancy term is electron domains. This is one electron domain, and it's this pair of electrons we're sort of referring to. This pair is an electron domain. 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 Over here, this pair, this pair, this pair are electron domains, and then that pair of electrons, that's also an electron domain. Just for some vocabulary for me to use while I talk. But the 4 things around them, 4 of them are electron domains. And we say they're tetrahedral. So there's sort of two layers. The first layer is electron domain. Yeah, you can come in and mess with that. There's two layers. I'll say the first layer, one, is electron domain. The second layer is molecular shape. For carbon, I'll go electron domain, tetrahedral. I'm just going to use tet for that. For this one, electron domain, tetrahedral. This one, again, you keep up with me here, because there's a twist. Now I need to go, what is the molecular shape for these? What is the molecular shape of these? Okay. I think it's easiest to start with nitrogen, just so you can see what I'm talking about with the molecular shape. This is the tetrahedral shape. It's, once you start trying to think in 3 dimensions, it'll wear your brain out very quick, trying to think that way. But you kind of have to think that way at least once just to see what I'm talking about here. But if you want a general way to describe what tetrahedral is, it's 4 spokes coming out from a central space, all equidistant from each other. There is a standard angle here. This angle, and this angle, and this angle, all these angles are equal to each other. So it's like 4 spokes coming out from a center, all equidistant from each other. Okay, so that's what tetrahedral is. I just wanted a quick description. So all of these are tetrahedral. The difference is, and then we will stick with nitrogen, 3 of these things are atoms, and 1 of them is a pair of domain, a pair of electrons. Okay, in the case where we're trying to figure out molecular shape, you start with the shape that you get from just looking at all the electron domains. You start that as your thought process, and you go, okay, now I'm going to ignore the pair of electrons. If I ignore the pair of, let's pretend this is the pair of electrons, and I'm going to take it out behind it. This is what I'm saying. You can picture a pair of electrons. Let me get another one. So let's pretend this little short thing is that pair of electrons. And I'm shortening it like that to tell you, in your mind's eye, you're going to ignore that part of the tetrahedral shape. All right. What is the molecular shape of this? These are actually, in all of chemistry, you'll hear me complain about some of the nomenclature, and I just think it's dumb that it's persisted this long. I like this one because they did something very simple. They didn't call it some special geometrical shape. What is your brain see? What would you be tempted to call that? Yep. Anybody else? What are you tempted to call that? Looks like a pyramid, right? We call it trigonal pyramidal because the base of it is a triangle and it looks like a pyramid. So it's very logical. The pyramids in Egypt have a 4 square base. So the pyramids in Egypt are square pyramid. We call this trigonal pyramid. There's your first molecular shape. Good marker. So put that in the notes, trigonal. I have always said pyramid. Pyramid. I think this is pronounced pyramidal, but I'm still going to say pyramidal because I can't help myself. But trigonal pyramid, that's the molecular shape. Its electron domain shape is, all of these are tetrahedral because they all have 4 things around them. So you begin with this same base shape. And then in your mind's eye, For this one, you ignore this pair of electrons, then you can see the pyramid. Okay. If I go on over to oxygen, yeah, it is, did I stick that in my pocket? Yeah. It is, if you consider the atoms and the electrons, that is the electron domains, all equivalent, yeah, it's still tetrahedral. We do draw this on a flat board, orthogonal like this, but truthfully, it's this shape. This, and this are really the same basic shape. But if I remove two of these to do oxygen, and I go, okay, those two spots are pairs of electrons. It started out tetrahedral, and it is still tetrahedral. But if in your mind's eye you ignore these two things, what are you tempted to call that? Compare it with...
linear or bent?
It's bent. We're going to get to this one because it's very simple. I just leave it till the end. But we call that linear, and if I bent that, it would look like this. That's what we call this bent. That's bent. So oxygen's molecular shape is bent. One simple little four-letter word, bent. Trigonopyramidal and bent. All right, when I get all the way out to fluorine, place one more of these. What do you think that shape is?
T-shape.
You're probably tempted. Well, it is linear. But really, that's kind of a null case. You don't tend to be asked about that one. Because there's only two atoms there. There's the fluorine and the atom. If you draw a straight line between those, of course it's linear. I'm going to say linear. Oh, this one. But I'm going to put it in parentheses because it's kind of a null case. And I think that'll be more obvious if I just keep going. But the point is, there's only two atoms there. Of course it's linear. It's possible to have three atoms and it still be linear. That's really the linear case. That's kind of a null case because if there's just two atoms, it's going to be linear. You don't tend to be asked about that one on standardized tests, and I kind of avoid it too, but I hope you can see that that's just like a null case. There's only two atoms, it's necessarily going to be linear between two atoms. It's when there's three atoms that it's special that it's going to be linear. Okay, let's do this row. Up here, three things around the atom. Yeah.
What was the location for carbon?
I was going to come back to it, but I'll go back to it now. Let's go back to the simplest case for tetrahedral. Where'd I put it? Where's my, there it is. Where's my null case? Put it here. Oh, I'm glad this model kit was down here. How would have taught this without the screens? Okay, back to all of these are this basic shape. It's just a matter of ignoring in your mind's eye to get pyramid, then ignore two of them in your mind's eye and you get bent. You get the last one, that's a null. This is tetrahedral by electron domain, and it's actually very simple. I dragged it out and made a big deal about it, but if none of these are pairs of electrons that you have to ignore in your mind's eye, it just defaults to tetrahedral. So the molecular shape for carbon in this case is tetrahedral. Molecular shape in this case is trigonopyramidal. The molecular case here is bent. Don't worry about that one, it's a null case. So you just revert to whatever shape it is if none of the electron domains happen to be in pairs of electrons. And it's going to be similar here. Oh, there's an atom I didn't circle. In this case, there are three things around it. In this case, all three are atoms. In this case, two of them are atoms and one of them is a pair of electrons. In this case, one of them is an atom and two of them are pairs of electrons. Notice there's two atoms there and there's two atoms there. This is the null case for this case. Three things are out. We call it, this one's second layer view is molecular shape. Yeah. One is the electron domain, two is the molecular shape. Okay, by electron domains, something that has three things around it looks like this. It's actually flat. It's not as complicated as tetrahedral because it actually fits in the plane of the board. I didn't draw this very good. I should have made this angle a little wider. But that pair of electrons and those two atoms have this shape. Those two pair of electrons and that atom has that shape.
So if it has a double bond, are they all on the same plane?
Yeah, they are still all on the same plane. You could just picture one of these as a double bond
Okay.
to an atom, and it still does this same shape. That we call planar because it's flat, and trigonal because you basically have a triangle. So tetrahedral, and then molecular shape, you have to consider things more. This one, I'm doing it like this. The electron domain for that, the electron domain shape for that, and then molecular shape I have over there on the individuals. So these are all tetrahedral by electron domains. They have individual things for the molecular shape. These are all trigonal planar. Trig, planar, trig, planar. Trigonal planar. Electron domains. Because there's three things around it. So that's this shape. Now we play this game again. This one is trigonal planar, and then its molecular shape, since there are no pairs of electrons, what do you think its molecular shape is? It's just like this one. There's no pairs of electrons, so it just defaults to tetrahedral. This one, the electron domain has the shape of trigonal planar. None of them are pairs of electrons, so we don't have to play that game with our mind's eye. So it just defaults to trigonal planar again. Planar. Here we have a pair of electrons. If I play that same game, in our mind's eye, we're going to ignore that pair of electrons. What are you tempted to call that? Bent. This one is molecular shape. Bent. Okay. In this one, if I replace another one of these, it's just two atoms, and yeah, I guess you could call it linear, but that's just a what I call it, kind of a null case. I'm going to put linear in quotes, because you're generally not asked about this, and you're generally not asked about this, because they're just, if there's two atoms, of course it's linear. There's nothing else it could be. Okay, and then, what did I do? Yeah, I did bend, and then I said, okay, this one, it's just two atoms. If those are a pair of electrons, it's just two atoms. So that's defaults to linear, sort of. Of course it's linear because there's only two atoms. Okay, that's that one. Next, I'm gonna do this is that null case again. I guess you could call this linear, but no one's gonna ask you about that, so I'll just say null case, maybe it's linear. But these are legit linear as their domain. And carbon never has any pairs of electrons around it, so these are by electron domain, two atoms, linear, and then by molecular shape for both of these is linear. So what this comes down to is carbon in this bonding situation will always be tetrahedral molecular shape. Carbon in this bonding situation will always be trigonal planar. And in either of these two, it's going to always be linear. Okay. Nitrogen in this bonding situation will always be trigonal pyramidal. This one will always be bent, and that's the null case. And really the last thing to pay attention to, these are the ones I'm saying you kind of don't have to pay attention to. They're kind of null cases. And then this one's bent as well. Really what I'm showing you is situations where the atoms follow the octet rule. I'm going to do some more where we still, remember I said starting with phosphorus you can have more than an octet around it. And all of these have an octet around them. Everything up here has eight electrons around the central atom. I'm going to do some other ones. For the expanded octet, there's only a few more. But what I'm getting at is, you could just kind of memorize that. If you see carbon like this, its molecular shape is tetrahedral. If you see nitrogen like this, its molecular shape is trigonal pyramidal. There is some logic in this that I've been explaining. But you can just about memorize those if you find these mess with your head. Kind of want to leave all that over here. Let me make it up. Well, I fixed one of them. Yeah, that one's completely. Well, we got one of the screens back. Oh, these are kind of abstract because I'm showing them just kind of by themselves. But if you had, yeah, let me point this out. I drew it like this. No, let me do this first. These have angles associated with them. The tetrahedral angle, if you say electron domain tetrahedral, 109.5 degrees. That's important. This is 109.5 degrees. This is 109.5 degrees. Because of the electron domain shape, don't worry about that. So those three that have the electron domain of tetrahedral, even if I ignore this in my mind's eye, this angle is still 109.5 degrees. It's still the tetrahedral angle. 109.5 is the only one that's kind of weird that you sort of have to memorize. The rest of them are very logical. So what we really say is this is tetrahedral, and the bonding angles, we call these bonding angles, between the atoms, its molecular shape is tetrahedral, and but that's really coming from the general idea of the electron domain. So really, molecular shape tetrahedral, bonding angle 109.5. Here we would say molecular shape, trigonopyramidal, bonding angle 109.5. So really that electron domain bit is just sort of one layer of logic that you kind of have to go through to see into all. But the angle comes from the fact that it was originally tetrahedral. So these four things are tetrahedral with each other. You just ignore two of them in your mind's eye, and you still end up with this bent shape, but the angle in this bent part is 109.5. So we would say oxygen in that bonding situation, its molecular shape is bent, and the bonding angle for that bend is 109.5. The rest of these are actually have a basic logic to it. Again, you get the angle from this electron domain idea. You think you can tell me what the angle is here? This you would need to do go to a geometry class and do a bunch of work to figure out what that angle is. This is obvious. It's in one plane. Going all the way around is 360. So each one of these is 120, 160. 360 divided by 3 is 120. So the bonding angle for trigonal planar is 120 degrees. So we would say carbon in this bonding situation is trigonal planar, 120 degrees. Same here, if we just ignored this in our mind's eye, yeah, we can call it bent, but it's actually bent at a different angle now. It's 120 degrees bent. This is bent at 109.5 degrees. This is bent at 120 degrees. And that's it, that's a null piece. So there's really, at this point, I've only given you 5 shapes and told you the atom they tie to. And if the ones below it are following the octet rule, you can actually kind of ignore all of these, because like I said, those are all molecules. Phosphorus, sulfur, selenium, and we get into some weird molecules that have Xe and some other weird things, but those are going to have the expanded octet. But if phosphorus, sulfur, selenium, and maybe silicon, if it's involved in a molecule, if they're following the octet rule, that is, they have 8 things around, then they're just like these. So it's just like the things above them. In linear, like I said, these are all very obvious. What do you think the bonding angle is for linear? What do you think that angle is?
180.
What is it?
180.
180.
Is linear for that like the name of the electron and
Yeah, it is. But usually when you're asked questions on these, you're asked what is the molecular shape. The idea of an electron domain is just sort of a piece of logic you go through to see into why all this is what it is. If there are 4 things around it, the shape that 4 things is going to make is tetrahedral. So you go through that bit of logic. So really, what I'm getting you to learn here is the molecular shape for this is tetrahedral, and these bonding angles are 109.5. Molecular shape for this is trigonoplanar, and the bonding angle is 120 degrees. I'm just using the idea of electron domain as a stepping stone to get us to that bit of logic. So, tetrahedral, 4 things around it, and you can end up as tetrahedral, trigonoplanar, and linear. Bent. There's bent, and there's bent at another angle. Yeah, I guess I'll put these in. I'm trying to make a little summary here. Trigonoplanar, 120 degrees. There's bent at 109.5 degrees, and there's bent at 120 degrees, and then linear at 180 degrees. If there's 4 things around it, 4 things. No, I didn't do this one. Trio planer and bent. There's three things to deal with for the 4 things case. 3 things. You got trigonal planar. What am I doing here? Oh, trigonal pyramidal. Trigonal pyramidal. I meant to do that one. And then bent 109.5 degrees. And then 3 things you've got. Trigonal planar, 120. Sorry. These are all 109.5 degrees because they're all tetrahedral at their base level. 3 things, these will all be 120 degrees. Trigonal planar, bent, both 120 degrees because when there's 3 things, it's 120 degrees. And then 2 things. Atom. Linear, 180 degrees. Okay. I wanted to leave those there because it's 2 things, 3 things, 4 things. And I want to erase this and deal with 2, 3, 4. There's 2 more of these electron domain shapes to show you. These occur when there's an expanded octet. Maybe I can squeeze them in over here. I have to erase everything. And I'll use phosphorus as a base case here. Now I'm using that's what I was going to look up. Let's see what's assume you have the Lewis structure in front of you that you can see. This book is just not great with examples. What do I want to do? Well, let me do this kind of in the abstract. So I'll say so there's the central atom. And let's say you have if you were looking at a Lewis structure written on a flat piece of paper, there's 4 things around it. I could have drawn it like that, but there's 4 things around it. Now I'm going to put 5 things around it. And 5 things is what we're doing now. Okay. If all of those things are atoms, The general electron domain shape here is called, let me see if you can see it. This is the shape. This one's a little weird because these three positions are different from these two. These are called equatorial positions. That's kind of, you can see the reference there, as if this were a globe, you've got an equator. And these are called axial positions, like the globe has an axis that it spins on. So they are two different types of positions there. But if all of them are atoms, you have this. And let me point out, if I just ignored this one, do you think you could see a pyramid there with the apex here, and then the base is also trigonal? But there's two of them. We call this trigonal bipyramidal. Kind of a mouthful, but that's the electron domain name for these. Bipyramidal. Okay. If you have the trigonal bipyramidal, and instead, and if all five things, here all five things are atoms, what if this were a pair of electrons? So now we have to play this game. If you have, five things, if all five things around them are atoms, then the five atoms, 0 pairs. If there are 0 electron pairs, it just defaults to trigonal bipyramidal. If there are 5 things, 4 of them are atoms, 1 is an electron pair, like that. Then it's still trigonal bipyramidal by electron domain, but this has a different name. And again, it is kind of one of those sensible names. All of these names are kind of whimsical. This, it's still a trigonal bipyramidal. But if one of those is a pair of electrons and we ignore it, we call this seesaw. Believe it or not, that's actually the official name for this. So it is still a trigonal bipyramidal. But if one of the equatorial positions is missing, we go seesaw. This is called seesaw. Seesaw shape. Seesaw. Here's a twist. I told you there are 2 different positions, and if one of them is missing like that, it comes from the equatorial position. Now, if 2 things are missing from this, you get I don't think we both did T-shape, so I won't. Let me double check. I guess y'all can see over there. This is the ones they mentioned. They don't do T-shape. I'm not going to do it. square planar. I don't think your book does it, so let me just skip that. So there's those four things around it. I'll say it, even though your book doesn't say it, just to be complete, because it's better. If there's 5 things, and 3 of them are atoms, and 2 of them are electron pairs, we call that we actually get back to trigonal planar. If 2 things are missing from this kind of depends on the size, and I think that's why your book ignores it. But if the electron pairs, if 2 of these are electron pairs, then they would be in the axial positions. That's what they do. They'll go to the axial positions. The electrons will necessarily go to the axial positions. In which case, if I remove these 2, yeah, if there's a pair of electrons there and a pair of electrons there, you actually get back to trigonal planar. The other trigonal planar didn't have any electrons there. There's no extra pairs of electrons here. There's 1 pair of electrons there to do Bennett. With this, when there's no electrons there, you've got this shape. When there's 2 pairs of electrons there, if 2 of these were pairs of electrons, then the 3 things that are left would be in the axial position, of the equatorial positions, and the electrons would be in the axial positions. Your book didn't mention this one, so I just wanted to say it. I think it's even possible, if 3 of these are pairs of electrons, they will end up around the equatorial positions, and you'll actually get back to linear. But I don't think your book goes into those 2 cases, so let me just kind of sneak past those. So all of them are atoms, it's trigonal bipyramidal. If 1 of them is a pair of electrons and 4 of them are atoms, you get seesaw. And we'll just stop there. Your book didn't go into it. But you can actually get trigonal planar if the axial positions are pairs of electrons. And if 3 things are pairs of electrons, they end up around the equatorial position and you end up back to linear. Okay, there's 1 more general electron domain shape to tell you. So under 5 things we have 5 things. If it's 5 atoms, it's trigonal bipyramidal. If it's 4 atoms and 1 pair of electrons, then it's seesaw. Let me show you the bond angles. This one's just weird because there's more than 1 angle, but you can totally see these angles. Again, the angles are very obvious here. What do you think the angles are for the equatorial?
109.5?
This, and this form a plane in the middle. And it's just like trigonal planar. That's 360 degrees. Forget this back one and this front one. That.
Oh, 120.
Yes, these are 120, just like the trigonal planar. So those are 120 bond angles. What do you think this bond angle is for the axial positions? That's 180. What do you think this angle is?
90.
It's actually 90. So you can actually totally see into what these angles are. And since there's several angles, I don't think you're ever usually asked those. You're generally not asked angles because there's not 1 angle that governs the whole thing. There's actually 3 angles here. There's this angle, 180. There's this angle, 120. And there's this angle, 90. If you actually have this in your hand, it's very easy to see that. If you're trying to picture in your head, it gets a little garbled. At least in my brain it does. But I guess I'll say, for For trigonobipyramidal, there's 120 degrees, there's 180 degrees, and there's also a 90-degree angle. There's actually 3 angles associated with trigonobipyramidal. The last one, 6 things. 5 things together, I'll do 6 things here. The general electron domain name for that is octahedral. And let me disambiguate a little bit. We went from 2 things around the central atom to 3 things around the central atom, 4 things around the central atom, then to 5 things around the central atom. Now we're to 6 things around the central atom. Yet I'm using the word octa. I'm saying octahedral, not hexahedral. So let me point something out. This wasn't called tetrahedral because there were 4 things, even though tetra is 4. The idea is if I put a plane, basically a triangular plane around these, and then a triangular plane around here, and then one here, and then one here, what I would have is a tetrahedron. It just so happens that a tetrahedron, you can make a tetrahedron out of a shape that has 4 spokes coming out from the center. So it's called tetrahedral because it's related to the tetrahedron. It really isn't related to the idea that there are 4 things. That's just a coincidence. But do use the fact that there are 4 things there to help you remember tetrahedral. But notice that isn't necessarily true of shapes, because if I took this and I put a triangular plane here and a triangular plane here and one here and one here and one here, then I would have an octahedron. That's why this is called octahedral. It just turns out that an octahedron would only have 6 of these spokes coming out. By the time you put planes on it, it would have 8 sides. So that's why this is called octahedral, because it's based on the octahedron. But there are only 6 things around it. For our purposes, it's a thing with 6 things around it. The octahedral shape is a thing that has 6 things around it. It's for our purposes. So maybe that helps. So here's the octahedral shape. So if you have drawn on a flat piece of paper central atom drawn as a Lewis structure, you would just see a central atom and then 6 atoms coming out of it. If you were looking at the Lewis structure of a thing that is octahedral, it will look like this. And again, we're cheating by drawing it on the board like this. Truthfully, it looks like this in 3 dimensions. If you were looking at one of these that had, instead of 6 atoms around it, 5 atoms around it plus a pair of electrons, the Lewis structure would look like that. It still has 6 things around it. But if you ignore one of those as a pair of electrons, that's what I'm talking about there. The thing that has 6 atoms around it, if it has 6 atoms around it and 0 pairs, we call the shape octahedral. If it's got 6 things around it, its electron domain shape is octahedral. If it's got 6 atoms, no, 5 atoms, 6 things around it, 5 of them are atoms, 1 of them is a pair, its molecular shape is, drum roll. If I ignore, say, this pair, let's say that's a pair of electrons down there, so I'm ignoring it. Can you see the pyramid? There's the apex and there's the bottom. Now it's like the pyramids of Egypt. We call that square pyramid. Square pyramid. I'll write it down. book go one more? Oh. Okay, I think your book just goes straight to square planar. Yeah, all right. I don't think your book does the square pyramid. So let me just kind of put a cloud around that. If it has 4 atoms and 2 pairs, square planar. Okay, if it's got 4 atoms and 2 pairs, it's kind of like the bipyramidal one. It's these axial positions, and if I'm ignoring these two, can you see the square planar shape? So if 4 of them are atoms and 2 of them are pairs of electrons, the pairs of electrons will oppose each other, and you'll get the square planar shape. Now let's talk about angle. This one only has one angle. Do you see it? It's equivalent. There's really no equatorial and axial positions, because you might go, hey, there's 4 equatorial positions and 2 axial positions, but then it'll go like that. You go, oh, no, wait, that's the equatorial and there's the axial. Actually, this is just totally equivalent. This isn't all that perfectly symmetrical. This does have equatorial and axial positions, and they're different. This one, they're all equivalent. So what do you think the one single angle governs this one?
90.
That's 90 degrees. So the angle associated with octahedral is 90 degrees. Which forces this octahedral to be 90 degrees, and this square planar to be 90 degrees. Your book didn't do this one. Your book does skip a few of these. They're a little obscure. But that's the diagram in your book. Your book has this, what's the name of that? Well, they don't give it a name, but it's right under representing molecular geometries on paper. There is this wedge. Let me show you that. The way you can represent these on paper is equivalent to on the board. It means on a 2-dimensional surface. How do you indicate these shapes on a 2-dimensional surface? I will erase these now. How you would draw these while trying to indicate the 3-dimensional structure. So it's kind of like drawing Lewis structures, but you're also trying to indicate some 3-dimensional structure. Atom, a molecule. Oh no, let me do this first. Nitrogen. So there's a Lewis structure. It's got its pairs of electrons where they're supposed to be. So let me ask you this. What's the molecular shape around this? Maybe I should have erased all those, but that's tetrahedral. What's the molecular shape here? Okay. This is screwy. I'm sorry we do it this way as chemists. But what you really wish I would do is draw this Lewis structure indicating a little bit of that shape. That's carbon connected to two atoms. There's one atom, there's another atom, with a double bond to another. Truthfully, a better way to draw this, if I'm being nice, this tetrahedral shape I can't do on a flat surface. But if I'm being nice to you, I will draw this as the trigonal planar shape to help your brain a little. But when you see Lewis structures, they're generally done in this neat orthogonal way. Chemists just like to do that. I don't know why. You more typically see it like this. Because when we're drawing these on a two-dimensional piece of paper, we already know we're going to run into situations where we can't really do it on a flat thing. So chemists just tend to go, okay, I'm just going to make it straight across and up and down. And then everything's connected to everything, and you can see it very easily. But this is carbon with two single bonds and one double bond. What I had drawn up here before, called that trigonal planar, and it is trigonal planar. I know it's not drawn trigonal planar here. What you need to think is carbon, two single bonds, one double bond. That's three things around it, three electron domains. So it's going to be trigonal planar. There's other tricks in here like that. This one's actually drawn the way you want it to be. When I drew carbon with double bond on one side, double bond on one side, what did I call that? Linear. Oh, this was what? So the bond angles here, I've drawn it as 90 degrees, but it's not. Do you remember what the angle was for tetrahedral?
109.5.
These are 109.5. You just can't see the 109.5 here because it's not three-dimensional. What were the bond angles for trigonal planar?
120.
120. This was linear, and it's, what's the bond angle? 120. All right. Carbon, two single bonds, one double bond. What's the shape? Trigonal planar. Bonding angles are 120 degrees. I've really fooled you here. You're going to look at that and you're going to, oh, that's linear. But chemists do this. They draw the OH just linear out like that. This is still at its base, four things around it, tetrahedral. Two of them are pairs of electrons, two of them go to atoms. So it's bent, and it's bent at the tetrahedral angle, 109.5. So don't let it fool you. What I had drawn here before, I actually had oxygen drawn like this. And then it was obvious that it was bent. And then the angle is the tetrahedral angle. So this is, the shape around oxygen is bent at 109.5 degrees. It's got four things around it, so its base electron domain shape is tetrahedral, which is 109.5. Then you ignore two of the spokes coming out, you have a bent shape. So the shape around oxygen is bent 109.5. But it's not drawn that way. Oh no, I'm missing some electrons. Yeah, okay. How many things are around this nitrogen? 4, so it's for its electron domain. But you ignore one of those pairs of electrons. Trigonal pyramidal. So this is trigonal pyramidal at 109.5 degrees. I know it messes with you because you wish this was drawn in a way that you could see the pyramid, but because it's flat, you can't see the three-dimensional structure. But that's nitrogen with three single bonds. That was trigonal pyramidal. And since its base shape is tetrahedral, the angle is 109.5. Here's nitrogen with a double bond, a single bond, and its pair of electrons. Do you remember what the shape there was?
Bent.
It was bent. If it was drawn a little nicer for your brain, I'll draw it like that. Maybe if I drew the pair of electrons out like that, you can see it. But trigonoplanar. So if its base shape is trigonoplanar, that makes this angle 120 degrees. So this is trigonoplanar at 120 degrees. 120? Yeah, 360. But this was the null case I kept saying was null. This is oxygen and only connected to one other atom. Of course, you would say that's linear, but really that's a null case. No one asks you about that. Same with hydrogen. Hydrogen only ever connects to one other thing. And same with all of these. They only ever connect to one other thing. So they really don't come up in the discussion in the way they're shaped. So when you see these in an actual molecule, they're not really drawn the way your brain wants to see them to give you that clue of what the shape is. But that's typical. Really, it's totally fair that chemists do this because trying to indicate that three-dimensional shape, the bigger the molecule gets, the harder it is because you're trying to take something that's ultimately three-dimensional and put it in 2 dimensions. So chemists just tend to default to this orthogonal way of doing things. Orthogonal means right angles. In some places it means regular angles or something, orthogonal. Like the orthodontist is trying to make your teeth go with right angles to your gums. Most of the other places that you'll see those larger shapes, octahedral and stuff, those tend to have one central atom and then atoms that radiate out from it. And you don't tend to see it in long chains like this. Okay, should I try to? No. I can do this because I have these. But if I don't have both screens, I really just kind of want to stop there. I know I've been shortening class lately, but we're actually well caught up. Your tests, I expect to have them by next Wednesday. I have some people who have had doctor's notes who still have to take the test. And I can't really give it back until I give it to them, and it's probably going to be Tuesday before they take it. But I'll get on that soon. So we're basically in chapter 5. We're going to cover pretty much everything in chapter 5 if you want to read ahead a little. But I will get to formal charge and resonance. I have to talk about polarity, which I haven't had. Yep. Y'all too. Have a good weekend. No, I'll put up an announcement that we're going to do on Wednesday. But I decided not to do it on Monday just to not throw it off. Okay, I'll make an announcement.
Okay, thank you. Wednesday.
Bye, Doctor.
Yeah, you too. You too. Questions?
Did you send me the link for the textbook at all?
No, I still need to set the hand.
Do you want me?
Yes, do that, because
Okay.
my deadline's full.
I'll go ahead and.
Yeah, I want you to have access to the book. Sorry about that.
No, it's.
That's crazy?
No,
No.
I think it'll probably be Wednesday next week.
Oh,